So now in this video I thought we would review parallel resistors again. This is an old diagram. But in any case, we're going to imagine we have an LED that we want to power with 12 volts right there. Most resistors are quarter-watt resistors, and so 1,000 ohms is about as much resistance as we want, or else the resistor is going to start getting a bit too hot. That's going to provide us about 10 milliamps of current, because out of that 12 volts, the red LED drops about 2 volts, giving us about 10 volts across 1,000 ohms for 10 milliamps of current, 0.01 amps of current. So what we can do, we could add another 1K resistor, but then that would be 20 milliamps of current. 10 milliamps would go through that one, 10 milliamps would go through that one. So instead, we could get 5 more milliamps of current by putting a resistor of twice that value. We're getting 10 milliamps, so 2,000 ohms of resistance there with 10 volts, because remember, red LED is dropping 2 volts, will give us 5 milliamps. So that's really easy mental math, and we have a formula for 2 parallel resistors. So you need a different formula for more than 2 parallel resistors. Not sure if I'm going to add that to this video or not, or do a separate video. But in case, when it comes to how much total resistance we have here, there's a relatively easy formula here. We can call that one R1, so 1,000 ohms times 2,000 ohms. We're going to call that one R2 right there. And then below it, you take those same numbers, but you add them instead of multiplying. So 1,000 times 2,000. So I already did the math down here. 1,000 times 2,000 over 1,000 plus 2,000 gives us 2 million over 3,000. So take 2 million divided by 3,000. We got 666.6 continuing on forever. So basically about 670 ohms of resistance. That's what that is equivalent to. We could use a single resistor of, somewhere, I'm not sure what, I think 680 is a value you might find. I think I might have 680 resistors. You could do that to get about 15 milliamps of current. But as we said before, 1,000 ohms is going to get pretty hot with 10 volts across it right there. Lower value resistor, it's going to get a lot hotter. And so we don't want to use a lower value. Instead, we can just connect them in parallel. Then we don't have to get a higher wattage resistor. It is pretty easy. And now we'll take the measurement. So I have the power supply set to 5 volts. We might as well measure that. So it's good to measure everything. And we got V for voltage auto ranging meter. It does everything. I just have to set it to V for voltage. I don't have to set a range. And it's kind of a tight spot to take a measurement right there. I don't want to accidentally touch that alligator clip. So in any case, there you can see we're just shy of like 12 volts, probably because we got a little resistance and stuff along the way. So our next measurement is going to be resistance. Again, auto ranging meter, all I have to do is set it to the omega symbol. So it's auto limits. That means there's a lot more resistance between these two probes right now due to the air than what it can measure right there. You can see we got pretty much 0 when we connect them together. So this is our 1,000 ohm resistor, and it looks like it's probably a little bit shy right there, unless the meter is a little off. And I don't have 2,000 ohm resistors, at least not in the main kit I use. I have 2,200 ohm resistors, and this one looks like it's a lot more shy than maybe it should be. Yeah, but in case, it's about 2,200. So now we're going to take the 1,000 ohm resistor, put it to the long lead, the anode of the LED, and then the positive supply. Now we're going to measure current. You got to be more careful measuring current. So very high current, you would move the red probe. There you can see all the other measurements. Red probe stays right there. So it stays right there. We'll be in the milliamp range for sure. And I think this goes up to 600 milliamps, this particular unit. And when it gets dark enough, the backlight turns on. So we have to complete the circuit. So going to the short lead, the cathode, and then the negative supply there. There you can see we got pretty much 10 milliamps of current. Right there it's saying spot on, 10 milliamps of current. And so that was the 12 volts, but the LED is dropping 2 volts divided by 1,000 ohms is about 10 milliamps of current. So This is about twice the resistance, actually slightly higher. So we should get a little less than 5 milliamps of current, but about 5 milliamps of current. That's added though, so we'll have probably like 14 point something milliamps of current, as you can see right there. That's what we got. So pretty straightforward. When they are in parallel, their currents add up. Make sure you turn the multimeter off when you are done. But like I was saying when we were looking at the diagram right there, since this is a quarter watt resistor, it will get too hot if we like raise the voltage, get more current going through it or whatever. Or if we use a lower value, it will get much hotter than you desire. So when you add resistors in parallel, each one of them is passing the current independently, so each one is creating its own amount of heat. And so it's a way to share how much heat or power is going through each component. They share them, so it prevents components from overheating. So if you have a problem where a component can't handle the amount of power that you need to put through it, it's really easy to just take a parallel component and have it take some of the burden off of the original component, as you see here.